going to start. We're going to start just talking about rational numbers. What do you think about when you see the word rational? Like, what is a rational number? You see the word ratio. Yeah, that typically jumps out to a lot of people. What do you think about? What comes to mind? Rational number. What numbers are rational numbers? Decimal. Okay, we'll write that. We'll be proving if some are or are not today. What else? What's a rational number? What else? Whole numbers? Okay. What other kinds of whole numbers do we deal with that we think are rational? Any other ideas for what makes a number rational? If a number is not rational, what is it?
Irrational.
What is it? Irrational. Yeah, we're a lot of what we've done so far this year has been working with rational numbers. In fact, there's not a single irrational number posted anywhere in this room. Any number that you see is rational, and there's reasons why. So we're going to start with the definition for what makes a number rational, and you don't have to write everything here down. What I want you to focus on is this section below. Yeah, as you begin to write, a lot of the information up here is very technical. A rational number is a number that can be represented as a quotient of two integers, which a quotient is division. And we know that division can be represented using a fraction bar, right? So really what it all boils down to is that a rational number is a number that can be written as a fraction. Now the key here, the little asterisk, is that the numerator and denominator would be integers. And that's mostly what we see. The key here is that they can be written as a fraction. You can probably think of a ton of numbers right now that would constitute as rational because they can be written as a fraction. You also may be able to think of a number that would be irrational because we cannot represent it as a fraction. Don't call out, but think about a value. Can you come up with one number that is irrational? And like I mentioned before, a lot of the math that you've done so far in middle school and even elementary school has been with rational numbers, numbers that can be represented as fractions. So as long as you have this bottom sentence here, that's really our main focus, that any number can be written as a fraction whose numerator and denominator is an integer, is a rational number. And you'll hear me say it a lot, rational numbers can be written as fractions. What are some examples of rational numbers? The number 1. Yeah, because we can write that as a fraction. What else? We have an integer. An integer is rational. What other kinds of numbers? Fractions. Yeah, give me an example. 2 over 1. Good. Or even like a partial, like 2/3. Good, that's rational. There's another kind of number that's rational that we're going to briefly talk about. We're going to go into more depth on Thursday, but we're going to briefly talk about it. Does everyone have this one sentence written?
Yeah.
Sentence? You didn't need to write the whole page, just the vowels. Okay, right. So up here we have some square roots, and we're going to focus a bit more on square roots on Thursday, but let's just take a look at what these represent. We have the square root of 16, the square root of 9, the square root of 4, and the square root of 1. These are called perfect squares. Why do you think we call them perfect squares? So when I find the square root, they give us an integer. They give us a whole number. The square root of 16 is 4. It's not like a crazy decimal, it's just 4. The square root of 9 is 3. The square root of 4 is 2. The square root of 1 is 1. Can you give me another perfect square? Can anyone give me an example of another perfect square? Yes. The square root of 144. Why is that perfect? What is the square root of 144? 12. Now we're going to talk a lot about irrational numbers and rational numbers, and so many people look at this symbol and they think, oh my goodness, if it's a square root, it has to be irrational. But that's not true, because the square root of 16 is 4. And if we know that 4 is rational, then the square root of 16 must also be rational. So our perfect squares are examples, and we point that out now. We're going to go into more detail on square roots on Thursday. Our perfect squares are rational. Okay? Can you give me an example of a number that should belong on this number line that would be irrational? What was that? The square root of, what was the number you said? 2.5. Sure. The square root of 2? Absolutely. Any square root that is not a perfect square is irrational. We're going to look into why that is on Thursday. When we're talking about rational versus irrational, I like to go over that symbol, because sometimes we think it must, if it's different, it must be irrational. So now let's get back to decimals. Okay, because we're talking about rational numbers today. We're focusing primarily on repeating decimals, but let's just start with terminating decimals. What does it mean? What do you think of when you think of the word terminate?
Jose Espinosa to the main office immediately.
What do you think of when you think of the word terminate? Terminate. When it stops, yeah, a decimal terminates when it ends. Right? And they can be written as fraction, right? We can write a terminating decimal as a fraction, and we can use place value. Let's take a look here. What would that decimal, that top decimal, be as a fraction? What would we call, well, what is that number if you said it? 4 tenths. How did you get tenths? Because it's in the tenths place value. Yeah, what would that be as a fraction?
4 tenths. What over 10?
4 over 10. Yeah, 4 over 10. Good. Now we can further simplify that. What does that simplify? 2/5. Good. How about this next one? What is that number? 75 hundredths. And hundredths because of that place value. And if we wrote this as a fraction? 75 over 100. Okay, good. How about the next one?
386 thousandths.
386 thousandths. And if I had to write that as a fraction? Good. We could skip one. So this is our numbers again with our fraction equivalent here. How do we know when we're writing a number as a fraction what number to use in the denominator? If we're going to put a decimal and we're going to write it as a fraction, how do we know what number to put in the denominator? Yeah, the place value is represented in our denominator. Now, when we write decimals as fractions, can I always simplify them? No, not necessarily. What if I had this number as a fraction? 3 over 10. And that already is simplified, right? I can't simplify it any further. Good. So now take a look here. There are 7 numbers up here. I want you to take 2 minutes, and I want you to write down which letters, like which numbers, so like A, B, C, D, E, F, or G, which ones are rational and which ones do you think are irrational? Okay. It's okay if you're not right on all of these, because there's a few other things we need to discover about the difference between rational and irrational. So let's take 2 minutes, take a look, just your best, what you think. If you had to decide on rational versus irrational right now for those 7 numbers. Don't forget, use that definition for rational as you're making your decisions. wants to share one that they believe is rational and a reason why they think it is. 9. B. Okay, why do we say B is rational?
Because the square root of 4 is
Yeah, the square root of 4 is the integer 2, and we know that 2 is rational because I can write it as a fraction. Good. Anyone have another example of one of these numbers that would be rational? Zara. A. Why is A rational? What is that as a fraction? 1/3. Yeah, I know that I can write that as a fraction. We know that 0.33333 is 1/3. Does anyone have another one? Laura. F. How do we know? Yeah, an integer can be written as a fraction, absolutely. Any others that we know are rational? Are any of the other numbers up there rational? Which one? G, how do we know? Yeah, we have this decimal here, but it is written as 1/7. They're the same thing, so it would be rational. Good. Any others? Which one? E or D? E, the number pi. Is pi rational? No, pi's not rational. Pi's actually irrational. We're going to talk about why in just a second. What about the other two? Are either one of them rational? Can I write either one of them as a fraction? Are they? D is rational. I can write that as a fraction. Because it would be 400. We could, if we had to, write that as a fraction. How about C? Rational or no? No, this is irrational. So why are I and E irrational? What is it about them? I and E? Oh, I said I because I just wrote that. C, sorry, and E. Why are C and E irrational? I wrote the letter I and it just stuck. Why can't they be written as a fraction? Well, integers are not the only numbers that can be written as fractions. Okay, so they're not terminating, meaning they go on forever. Okay, but the problem with that is A is a non-terminating decimal and A is rational. So what? So yes, if we're talking about irrational, they go on forever. But there's something else. That's what it means to be irrational. So we're looking for reasons, not just repeating the definition. Which means they don't what? The numbers, yeah, the numbers aren't the same, meaning the numbers never repeat. They're non-repeating. So the most common irrational that we've worked with so far would be pi. We haven't done a lot this year, but last year we did. Irrational numbers, they go on forever. The decimals never terminate, but they never repeat. So like a number like 0.333, we can write that as a fraction, and the rest of our time today is going to be spent learning how we write a repeating decimal, non-terminating but repeating, how we write that as a fraction. So we're going to use that as our example because we already know that 0.3 repeating is 1/3. Okay, so use that information as we transition here. Okay. So first, let's start with this. Explain to me why, if I do that subtraction problem, I'm left only with 3. When I do the subtraction, what happens? What am I eliminating? Yeah, this repetition. Now the 0.3 with the bar, who remembers what that symbol means at the top? That's the number that's repeating. If I wanted to break it out, it would look like this, and it would just never stop. So imagine this. If we did this subtraction, and it just kept going. So if I did a subtraction problem of that, the reason, you can probably see it a little bit better now, if I subtract, I'm just left with 3 because the repetition, that repeating decimal, is really eliminated, right? It's gone. If I have 3 point all that, and I subtract just point all that, I'm just left with a 3. And so we're going to use this to help us solve for this, not solve, we're going to use this to write our repeating decimals as fractions. So if we wanted to convert our repeating decimals to fractions, what must we get rid of? What do we need to eliminate in order to figure out a value? Yeah, the decimal part. We need to get rid of that repetition. So here's how we're going to do it. So now let's talk about this up here. We're going to begin by creating an equation. So we're going to turn 0.3 repeating into a fraction. And we're going to start by writing it as an equation. Does anyone have any idea why we might want this to be an equation instead of like just a number if we're going to try to do some stuff to change it around? If I manipulated a number, did I change the value? Like if I multiplied a number by something, did I change the value? What happens if I multiply that equation by a number? Does the value for x change? No, like I can multiply both sides of an equation by 10. It doesn't change the value of x. But the problem is, if I just left it as 0.3 repeating and multiplied it by 10, I've changed the value. So we want to begin here with an equation, because we can manipulate an equation to do whatever we want without changing the value of our decimal, which is ultimately going to be our fraction. So now when we're dealing with this equation, what decimal place, where does the repetition begin? What decimal place? In the tenths, right? It's just that 3 repeat. So I'm going to multiply both sides of this equation by 10, and I'll be left with 10x equals 3.3 repeating. I have not changed the value of x in any way because I multiplied both sides by 10. Is there a way, and I want you to think back to our unit that we just finished, where we worked with elimination. In the last unit, we were eliminating a variable, but here we want to focus on eliminating that repeating decimal. Is there something I could do with this equation to get rid of the repeating decimal? And think about what we did in systems when we eliminated. What did we do in our unit on systems of equations to eliminate? Okay, we did the opposite, we subtracted, but what else do I need here? I have this equation here. What else what would I need? Because right now I have nothing to calculate. I have nothing to take away. Another equation. Exactly. Say that loud. I would need another equation. What other equation do I have? If you subtracted, what would I be left with? I'd be left with 9x. What happened on the right side? I'm just left with the 3 because this eliminated. Can I solve for x?
Yes.
Yeah, I would divide by 9. So what's x? X is 1/3. So this is how we can go from 0.3 repeating to the fraction 1/3. You're going to see it on the next slide. I have the steps broken out. All right, and this is what you're going to write down. Okay. So this is how we do this. We begin first with our equation, right? And I know that that's not actually written into your steps, but if you want to make that a little asterisk at the top, but the first thing, you really want to use an equation, because you can manipulate an equation without changing value. If you were only dealing with the number, you'd change values if you multiply or divide or anything. So we have x equals 0.3 repeating. Now the first thing we're going to do, which is represented here, we're going to multiply by a power of 10. What are some powers of 10? 10, 100. 1,000. Yeah, why do you think we would multiply by a power of 10? What happens like with the decimal when we multiply by a power of 10? It will, yeah, it'll make our number like larger, and it keeps our number intact. It just helps we're able to move that decimal to represent that multiplication of 10. Then the second step would be represented here. When we subtract the repeating decimal and its corresponding value on the other side. So we repeated that 0.3 repeating and the x. That's really a version of elimination, like our last unit. And then the last step, once your repetition, the repeating decimal is gone, you can solve for x, or the variable, whatever variable it is. Now this is a good example to have. You should have this example in your notebook. We'll go through when you're practicing, you can use this example to refer back to. We're going to do a problem on the next slide using this information, and then we're going to go through one other, just so you can see the next level up in terms of, I'll say difficulty, but another version. Does anyone need more time writing these 3 steps down? Are we good? We'll go through these 3 again, so don't panic. Let's try this one together. If we begin with an equation, how am I going to begin to write this as a fraction? What do I need first? Look at everything you wrote down. What would the first thing be? I want to multiply by a power of 10, right? What am I going to multiply by? 1,000. If I multiply by 1,000, look what happens here. And for some, you might need to see it this way. That's really what the number is. I just eliminated the bar. When I multiply by 1,000, it becomes... There's a few things that are really important here. The key is that I know when I do subtract, I'm going to be able to eliminate the repeating decimal, because what's in my decimal place, what starts in my tenths spot, right, in this place value, is that repeating portion. If I only multiplied this by 10, I would be left with this number. And the problem is, if I did subtraction, this is an issue. Right? This would be a problem, because it won't eliminate, and I'd be left with a decimal. So that's why I don't want to multiply by 10. I really want to multiply so that the only thing left in my decimal places can be represented by the repeating portion of my decimal. Now, once I have this written, I multiply 1,000. I have 1,000x equals 512.512 repeating. What do I do now? subtract the other equation, which would give me 999x, and it equals 512. And lastly, to actually find the fraction, what would I do? Divide by. So that would be your fraction. Maybe not. So what did we do? We actually manipulated the equation so that we can eliminate our repeating decimal. And from there, once we had a whole number, we were able to solve and get our variable by itself. And there's one other kind of problem, right, that might be, we're going to turn the repeating decimal into a fraction, but it's a little different, okay? And that would be this. So what's going on with this decimal? The repetition starts in the hundredth spot. So this number, if you broke it out, actually looks like this. Okay, so what would we multiply by?
10.
Okay, if we multiply by 10, we'd be left with 10x equals 5.6 repeated. Now what? So what's going to happen if I subtract my original decimal? What's happening when I subtract my original? Does it eliminate? No. Okay, so this equation, so we had multiplied by 10, we have 5. This equation, I can't use that one. That's not really helpful. So I need another equation. What else could I do? This one's not really helpful for me because I'm not going to be able to eliminate that decimal. So what else could I do? I need another one. I can multiply by 100. If I multiply that equation by 100, I get this. Could I subtract it now? Yeah. What would happen? What would I have on the left? And on the right? So I want you to take a look at that one again. Our original number was 0.56 repeating. We knew that we needed to manipulate that equation so that the only thing left in our decimal places was the repetition. So we multiplied by 10. The problem is I really couldn't use my original equation to subtract because of this. That number really prevented me from using that whole equation because my repeating decimal wouldn't have eliminated it. It would have been a problem. So instead, I came up with another equation. I can use another power of 10, right, which we used, Zara recommended using 100. If I multiply both by 100, then the only thing left in my decimal places would have been the repetition, and I can go from there. So this would probably be like your more complex of problems. It really does depend on what is repeating, right? You might see some like this one, or like that would change, right? And it depends on what you would multiply by. Depends on what is repeating. We'll see some examples. Okay. Does anyone have questions about this example we just went over, which is a great one to have written down, or the original one we practiced up here with the 512?
So the first step you would multiply by 10 and then you would subtract that by the 100.
Yes, so what happened was when we first learned how to do this, we knew just we multiply one time and we subtract the original equation. The problem in this one is that the original equation is not really helpful to us because it will not allow us to eliminate the repeating decimal because our original decimal wasn't only repeating, right? That 5 was like hanging out in there, and that would be a problem. So instead, we still needed that second equation. So we came up with another power of 10. That would have just left our decimal place values as the repeating portion. You'll see examples on the little activity that you have up here. So we're going to practice a little bit of this. I'm going to slide to the next slide and explain to you what it is we're going to do. Does everyone who wanted this written, do you have it? Okay. I'm going to pause this and then we're going to, I'll show you what we're going to do.